Welcome to Cambridge IGCSE Physics, Lesson 22.1, Thermal Radiation Basics. This is core content for the Cambridge IGCSE Physics syllabus 0U625. Today we explore how all objects emit thermal radiation, which is infrared electromagnetic radiation that requires no medium for transmission. This fundamental concept explains heat transfer through space and forms the basis for understanding thermal imaging, solar energy, and many everyday phenomena. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, know thermal radiation is infrared radiation. This means understanding that thermal radiation is part of the electromagnetic spectrum, with wavelengths longer than visible light. Second, know all objects emit thermal radiation. Every object above absolute zero temperature emits this radiation continuously. Third, understand radiation doesn't require a medium. Unlike conduction and convection, thermal radiation can travel through vacuum. These objectives align with Assessment Objective 1, which tests scientific knowledge, and Assessment Objective 2, which tests application of concepts. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, thermal radiation, which means infrared electromagnetic waves emitted by objects due to their temperature. All matter above absolute zero emits these waves. Second, infrared, which means electromagnetic radiation with wavelengths longer than visible red light, typically between 700 nanometers and 1 millimeter. Third, electromagnetic, which means energy transmitted as oscillating electric and magnetic fields through space at the speed of light. Understanding these terms precisely is crucial for exam success and practical applications. Let's explore our first core concept. What is thermal radiation? The fundamental principle states that all objects emit thermal radiation continuously. This means every object above absolute zero temperature, which is minus 273 degrees Celsius, emits infrared electromagnetic waves. The definition is thermal radiation is infrared electromagnetic radiation emitted by all objects above absolute zero temperature. The key properties include wavelength range from 700 nanometers to 1 millimeter, speed in vacuum of 3.0 times 10 to the power 8 meters per second, and no medium required for transmission. The diagram illustrates a hot object emitting infrared radiation in all directions. Notice how the waves travel outward without needing air or any material medium. This principle is fundamental because it explains heat transfer through space, including solar energy reaching Earth. Now we examine the universal property that all objects emit thermal radiation. This follows from the kinetic theory of matter. Every object contains moving particles, and accelerating charges produce electromagnetic radiation. The temperature dependence shows that hotter objects emit more radiation with shorter wavelengths. At room temperature, objects emit infrared radiation, invisible to our eyes. At 500 degrees Celsius, objects glow red. At 1000 degrees Celsius, they appear white hot. Even ice at 0 degrees Celsius emits infrared radiation, though less than warmer objects. The human body at 37 degrees Celsius emits infrared radiation, which thermal cameras can detect. The diagram shows how all objects above absolute zero emit radiation, with intensity increasing with temperature. Let's work through our first example. The problem states, explain why thermal radiation from the sun reaches Earth through space. We are given that space between sun and Earth is mostly vacuum. We need to explain this using thermal radiation properties. Step 1. Identify the radiation type. The sun emits thermal radiation, including both infrared and visible electromagnetic waves. Step 2. Apply the key property. Thermal radiation requires no medium for transmission, unlike conduction, which needs direct contact, or convection, which needs fluid movement. Step 3. Explain the transmission. Radiation travels through vacuum at 3.0 times 10 to the power 8 meters per second. Step 4. State the conclusion. Solar thermal radiation reaches Earth despite the vacuum of space, because electromagnetic radiation can travel through empty space. Example 2 compares thermal radiation from objects at different temperatures. The problem asks us to compare thermal radiation from hot and cold objects. The data shows hot iron at 500 degrees Celsius and cold iron at 20 degrees Celsius. Now we analyse systematically. First, both objects emit radiation. This follows our principle that all objects above absolute zero emit thermal radiation. Second, the hot iron emits more radiation. Higher temperature means greater radiation intensity. Third, the hot iron glows visibly red. At 500 degrees Celsius, the iron emits visible light as well as infrared. Fourth, the cold iron emits only infrared radiation, invisible to our eyes but detectable with thermal cameras. The diagram shows the hot iron emitting intense, visible and infrared radiation, while the cold iron emits weaker infrared radiation only. Mathematical skills are crucial in thermal radiation physics. Let's examine 3 key skills. First, wavelength and frequency relationship. The equation C equals F lambda relates wave speed, frequency, and wavelength, where C is the speed of light, 3.0 times 10 to the power 8 meters per second. For infrared radiation with wavelength 1000 nanometers, the frequency equals C divided by lambda, giving 3.0 times 10 to the power 14 Hz. Second, temperature conversion. To convert Celsius to Kelvin, add 273. For example, 27 degrees Celsius equals 300 Kelvin. This is important because many thermal radiation equations use absolute temperature. Third, scientific notation. Large numbers like the speed of light are written as 3.0 times 10 to the power 8 meters per second. Small numbers like infrared wavelengths are written as 7.0 times 10 to the power minus 7 meters. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, state what type of electromagnetic radiation is thermal radiation. This tests your knowledge of the definition we learned. Question 2 is intermediate level. It states, explain why a hot cup of tea cools down in a vacuum. This requires you to apply the concept that thermal radiation doesn't need a medium. Question 3 is advanced level. The question asks you to compare thermal radiation emission from objects at 100 degrees Celsius and 200 degrees Celsius. This tests your understanding of temperature dependence. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how thermal radiation applies in practice. In medicine, thermal imaging cameras detect infrared radiation from the human body to identify areas of inflammation, poor circulation, or other medical conditions without invasive procedures. In astronomy, infrared telescopes detect thermal radiation from cool stars, planets, and dust clouds that don't emit visible light, revealing hidden structures in the universe. In energy technology, solar panels and thermal collectors harness thermal radiation from the sun to generate electricity or heat water. These applications show why physics matters. Career-wise, physics knowledge leads to many professions. Biomedical engineering uses thermal imaging, aerospace engineering designs infrared sensors, research advances our understanding of radiation, and the technology sector develops thermal management systems. Let's review the solutions. For question 1, the answer is thermal radiation is infrared electromagnetic radiation. This demonstrates knowledge of the key definition. For question 2, the tea cools by emitting thermal radiation into the vacuum. Radiation requires no medium, so heat transfer occurs even without air present. This shows understanding that thermal radiation is different from conduction and convection. For question 3, the object at 200 degrees Celsius emits more thermal radiation than the object at 100 degrees Celsius. Higher temperature produces greater radiation intensity and shorter wavelengths. This demonstrates understanding of temperature dependence. Now, exam success tips. First, always show you're working even for simple questions. Second, include units in every step. Third, use key physics words like infrared, electromagnetic, and no medium required. Fourth, read questions carefully. State means give a fact. Explain means give reasons. Compare means identify similarities and differences. Let's summarize today's lesson on thermal radiation basics. The key points to remember are: first, the definition. Thermal radiation is infrared electromagnetic radiation emitted by all objects due to their temperature. This radiation has wavelengths longer than visible light but shorter than radio waves. Second, the universal principle. All objects above absolute zero temperature emit thermal radiation continuously. Even ice cubes emit infrared radiation, though less than hot objects. Third, the transmission property. Radiation travels through vacuum at the speed of light, requiring no medium unlike conduction or convection. For further study, review the electromagnetic spectrum to understand where infrared fits. Practice temperature conversions between Celsius and Kelvin. The next lesson covers heat transfer methods, comparing conduction, convection, and radiation. Ensure you understand today's concepts before moving forward, as thermal radiation is one of three fundamental heat transfer mechanisms.